Modern digital infrastructure, from the phone in your hand to the servers routing global finance, relies on one simple mechanical concept: the switch. Since the earliest computers utilized these massive tape drives, we have processed all human information through binary logic. Billions of switches turn on and off, creating the ones and zeros that render every email and transaction. Inside a microchip, electrical charges split sharply into these geometric paths. This rigid physical structure creates a ceiling on our computing power, as simple binary gates cannot process the complex, fluid probabilities found in nature. We have reached the limit of what these switches can do. To build a secure, light-speed network, we have to move beyond the binary framework entirely. The foundation of this next network is the quantum bit, or qubit. A qubit does not choose between 0 or 1. Through superposition, it exists as both at the same time. While a coin is spinning, it is neither heads nor tails, but a blur of both probabilities at once. That fluid state provides incredible processing power, but it creates a massive engineering hurdle. A qubit in superposition is impossibly fragile. At a microscopic level, heat is physical vibration. If even a tiny amount of thermal noise strikes the qubit, as shown in this diagram, the wave state shatters into chaotic particles and the data is lost. This is the central paradox of the quantum internet. We are building the ultimate communication network, yet our warm, noisy environment is constantly destroying the data. To protect a qubit, engineers must create artificial pockets of space where the normal laws of thermodynamics are essentially paused. This requirement led to the development of the dilution refrigerator. Its tiered structure uses these dense arrays of cooling loops and coaxial cables to strip away thermal energy. Each gold-plated stage is a step toward absolute stillness. This assembly functions as the most extreme isolation chamber ever constructed on Earth. At its core, the temperature drops to 0.01 Kelvin, just a fraction of a degree above absolute zero. This environment is significantly colder than the dark side of Pluto or the empty vacuum of interstellar space. At this extreme, thermal vibration stops. Matter reaches a state of absolute physical silence. This artificial silence allows a fragile qubit to maintain its superposition without being disturbed by the surrounding universe. Building a global internet entirely on massive gold towers isn't practical for standard server rooms. This has led to a primary alternative, using synthetic diamonds to house quantum data. Scientists create a nitrogen vacancy center by removing a carbon atom from the diamond's lattice and replacing it with nitrogen. This creates a microscopic atomic trap. The rock-hard crystal matrix locks a single electron spin in place, shielding the quantum information from noise without the need for absolute zero temperatures. Whether we use massive refrigerators or microscopic crystals, the goal remains the same: isolating information from the physical noise of reality. These engineering feats are more than just cooling experiments. These extreme environments provide the only safe zones where we can successfully harness subatomic laws for communication. Within these isolated nodes, we can perform quantum teleportation. A particle state dissolves in one location and rematerializes perfectly in another, moving the data without any physical signal crossing the space between them. Mastering these absolute extremes has allowed us to move information through the very fabric of space. It is the transition from a network of copper and light to one built on the fundamental behavior of the subatomic void.